Okay, hopefully we've transitioned into this part of the video without too much clumsiness, but let's get down and dirty with this central limit for sample means. What I want you to point out to your students at this juncture is that the rest of the class, and I always get real dramatic here and tell them that the rest of the class, once you get into big boy, big girl stuff, the rest of the class deals with the dynamics between samples and populations. And what we want to do is we want to look at both directions. Now let me go to the next screen and make this a little bit neater. And so we're looking at the dynamic between a sample and a population, and I want to look at both directions. So if we're looking at this direction where we take a sample and use it to make a statement about a population, then this is referred to as inference. The sample is known. We collect it. We can find the mean of it. We can find a standard deviation of it. We can look at a histogram of the sample. We can look at a box plot. But what we're trying to make an inference about is unknown. The other direction is called probability. For some reason my eye doesn't want to happen right there. I don't know why. Let me draw it in there. So probability. What probability is, we're given information about a population and we want to know the likelihood of getting a particular sample from it. As in this situation, the population is known, but the sample is unknown. For example, take a deck of cards. Let that be your population. You know a standard deck of cards has 52 cards, 4 aces, 4 kings, and so on and so forth. Aces, diamonds, clubs, and hearts. If we choose a couple of cards at random, we don't know what we're going to get. The result is unknown. But using probability, we can determine the likelihood of getting a particular sample. For example, what's the probability of choosing a card at random and it being an ace? Well, there's 4 aces in a deck. We know out of 52. So if you like reducing fractions, it would be 1 out of 13 or 4 out of 52. We can only calculate that probability because then we know the deck from which we're drawing our card. Now imagine I walk into a room with only 4 cards, but I don't tell you what they are. Population's unknown. I don't know what I'm drawing from. Can I determine the probability of getting a particular card from a deck that I don't even know what cards make up the deck or make up the 4 cards? I can't, because again, the population is unknown. Now, arguably the most important branch of statistics is inferential statistics, but everything that we do up here relies on chance, random chance, probability. So it's important that we fill in the blanks here via the central limit theorem and sampling distributions, so it leads into a solid framework for inferential statistics. Now, central limit theorem for sample means. This is kind of a good way to think about it. First of all, let's just assume that we begin with a population that has a particular mean and standard deviation, both that are known. So the mean and the standard deviation. Guys, I don't know what's going on, but I can't write on that particular part of my board. Now, some things that happen from here on out. Depends on what the shape of the distribution is. So if we have a not normal distribution or a normal distribution, we get into sample size differences. If we have a normal distribution, we only need a sample size 2 or bigger. And if we have something that's not normal, and what I want you to think about here and communicate this to your students, a skewed distribution, then we need a sample size of 30 or bigger. So guys, consider this to be a big brick wall. We can only go on past the brick wall if this sample size restriction is satisfied. So if it's satisfied, I want you to get your students to start thinking about collecting random samples. So the first thing I want you to do is think that you set your sample size. And if you're trying to teach this to a group of high school students, even college students, and you just say n, I don't think it's going to be really clear. So let's just come in and decide that n is 34. So we set it. So throughout this entire example, I'm going to talk about n being 34. So n is 34. I want to go into my population, and I want to pull out 34 measurements, and I want to add those 34 measurements up and get my first sample mean. Throw those 34 back in the mix, pull out another 34 at random, add those 34 up, divide by 34, and I want to get my second sample mean of size 34. Guys, do it again. Do it again. Imagine doing this forever. Well, guys, if you could do this forever, what would you have? Well, you'd have a bunch of sample means. Well, guys, I don't know why, but this isn't letting me write right there. And anyway, what we would call this, go on the other side, we would call this the distribution of sample means. Okay, I've got a bunch of sample means. And it would seem reasonable after I get this distribution of sample means to ask some intelligent questions. What's its shape? Where will the distribution be centered? And the most important question probably, how do I define the variability? How do I define the spread within the distribution? Well, this kicks in the central limit theorem. And the central limit theorem tells us the answers to those questions. What's the shape? Well, you'll have a normal distribution. What's the center of the mu sub x bars? Now let's think about that. Students are going to freak out when they see that because to them x bar is the mean and mu is just something crazy that Dr. Darbro threw at them at some random spot within the semester. What you need to get them to understand here is the mean mu stands for the population of the sample means. Therefore, we put the x bar as the subscript to say that we're looking at the population of all mean of all the x bars. So in other words, if I can go back here and if I could take x bar 1 plus x bar 2 plus x bar 3, all of these, and divide by a very huge number. I know this is horrible, but if we think about it forever, so that's just too ugly for me to even include there. But imagine we had 100,000 sample means. What if we divided by 100,000? Well, we would get a population mean of all of these individual sample means. Well, that's exactly what I'm talking about here. Central limit theorem tells us that's going to be exactly equal to the mean that we started out with way back here. Next thing is the shape. Well, the standard deviation of the sample means. Central limit theorem tells us that it's going to be sigma, which is this value right here, divided by the square root of n, which we set right here, which is 34. Now guys, we give this a very important name called the standard error. Okay? Guys, pros at this now, right? Okay. I tell you what, let's get out of this and go into a handout that I give my students, and I want to work through that with you. Let me get things. I've got my headphones all messed up here. Here we go. Let me work through this with you, okay? So I want to do dual screen so I can bring the calculator up and show you how we do this stuff on the calculator. All right, cool. And cooler. All right, guys. First problem. You draw many samples of size n equal 15, so we're setting it size 15, from a population that is normally distributed. Remember, if we have a normal distribution, sample size just needs to be 2 or larger to examine the distribution of sample means. So we have a population mean of 120 and a population standard deviation equal to 20. What are the values of the mean mu sub x bar and the standard deviation sigma sub x bar? Well, guys, obviously the mean is going to be 120, and the standard deviation will be 20 divided by the square root of 15. Oh, I've got a new calculator here. All right, so 20 divided by the square root of 15. So the standard error, or the standard deviation sigma sub x bar, would be 5.16. Sketch the distribution of sample means using the 68, 95, 99.7% method, or the rule. I don't know why I said method. So let me write down something before I go to the other. The other page here. So mu sub x bar is 120, and let's just say sigma sub x bar is 5.16. All right, guys, let me get out of here. Go back to this. So, guys, the 68, 95, 99.7% rule. Well, we know smack dab in the center is going to be 120, and one standard error above the mean is 125.16, and one standard error below the mean is 114.84. So guys, 68% of the sample means will be between here and here. It would be very easy to go ahead and do the 95% just by adding and subtracting 5.16 from the, adding it to the 125.61, which would be 130.32. And down here we would have, what, 109.68. So guys, between here and here, we have 95% of the sample means. So the answer to that is really just a matter of appreciating the fact that we're no longer working with the standard deviation, we're working with the standard error, and we just need to, be able to add, multiply, add, and subtract. Okay, what is the probability? No-brainer. Get your guys thinking. Get your students thinking. What is the probability? Starts with P. Use the P key. That one of the randomly selected samples of size n equal 15 has sample mean above 132. Well, above 132 means that my lower bound is going to be 132. My upper bound is going to be E99. My mean is 120. Now students here are going to want to just type in for standard deviation 5.16. Try to impress upon them that you get a better answer if you'll just go ahead and type this in. Okay? Paste. Hit enter. So the probability would be 0.0101. Okay, part D. What sample mean of size 15 is located at the third quartile? Well, guys, I'm not asking the student here to find a probability or a proportion or anything that starts with P. I'm asking them to find a particular score. We know that this particular key, the inverse norm, works with area below, and we're focusing on the third quartile. So we should know by now that the area below the third quartile is 75% or 0.75. Again, the mean is 120. The standard deviation is 20 divided by square root of 15. So guys, the sample mean that represents the third quartile is 123.48. Now, the next question gets a little tricky. Not too bad. So the next question deals with teacher salaries at a very large school district. Says they're positively skewed. Now guys, remember, positively skewed, we have to have sample size 30 or bigger to be able to calculate probabilities. So, part A, describe the shape, center, and spread of the distribution of sample means when drawn 15 at a time. I don't know. Don't know the answer to it. We start with a positively skewed distribution. The central limit theorem doesn't actually kick in and tell us we have a normal distribution until we get sample size above 30. Actually, it works much, much better once we get up to 50 and even at 100. But 30 isn't bad. So part A, I have no idea. Can't do that problem because the central limit theorem doesn't work for a sample size of 15 when we have a positively skewed distribution. Part B, describe the shape, center, and spread when we have a sample size of 75. Well, shape, normal distribution. Center is going to be 65,000. And the standard deviation is going to be 15,000. Divided by the square root of 75. So guys, the standard deviation, which we call the standard error, which represents the spread, will be 17,320.51. All right, gang, part C. If 75 teachers are randomly selected, what's the probability? Starts with a P, no brainer. Get your students thinking. P key. So probability, their average salary. Hold on now, I can't see this here. Okay, so their average salary is between 62,000 and 64,000. Mean is obviously 65,000. And a standard deviation is going to be 15,000. Students will always want to stop there, so stay on them. Remember, we got a sample size of 75, so we have to account for that. So the probability would be 0.2402. All right, part D, what's sample mean of size 32? So we're still above the threshold of 30, so we can work the problem. What's sample mean of size 32 is located at the 95th percentile. So guys, we're looking for a sample mean, not something starting with a P. So we use inverse norm. 95th percentile says 95% of the distributions below. The mean is obviously 65,000. And a standard deviation will be 15,000. Divided by square root of 32. Alright gang, go for paste. Make it happen. So the average of 69,361.58 would be at the 95th percentile. Alright guys, calculate and interpret the Z-score for a sample mean of 70. Well guys, remember the Z-score is the average of the sample or the sample information minus the mean of the population divided by the standard deviation, but guys, in this case it'll be the standard error. Got to get your students thinking about a couple things here. First of all, you got to get them thinking about order of operations, hence make sure you put that parentheses in front of the 15,000. And what do we got here? 40 teachers. And get them thinking about standard error instead of standard deviation. So guys, the value for the Z-score would be 2.11. So what we would say here, and I'm going to type this out because this is critical, so 2.11, right? So what we would say here, we would say a sample mean of 70,000 when taken from N equal 40 teachers is 2.11 standard errors above the mean. So guys, You have to tell the sample mean. You have to tell how many teachers or how many subjects or how many measurements created the sample mean. And then it's important to realize we're dealing with standard errors and not standard deviations. Guys, that's all I got. This is kind of a short video, so have a good one.